Yeah.
Okay. Yeah, go ahead, Vishnu.
Yes, sir. Okay, so good evening, everyone, respected faculty members, and dear friends. It is my pleasure to welcome you all to today's expert session on microcontrollers and embedded systems and the Judge framework. We are honored to have with us Mr. Ketan Bhaidasna, a research engineer and inventor at Halliburton Energy Services, Houston. He specializes in developing advanced engineering solutions like automated systems and intelligent sensors that provide real time data and improve efficiency in complex operations. With multiple US patents and impactful innovations, he has successfully bridged the gap between research and real world applications. We are truly privileged to have him with us today. Now, I warmly invite Mr. Ketan Bhaidasna to begin the session. Sir, over to you.
So, Vaishnavi, is everyone able to hear me fine? Hello?
Yes.
Okay, very
Yes,
good.
Yes,
sir.
sir.
Okay, let me share my screen. Let's so that get this out of the way. There is a share button, and let me share my screen. You are screen sharing. Okay, we're good. Uh, Everybody can see the screen?
Yep.
Yes, we can.
Yes,
Okay, very
sir.
good. Very good. Okay, thank you very much. So, thank you for that great introduction, Vaishnavi. You did fabulously good. I've never had this privilege of somebody saying so many kind words. Thank you very much. Um, so we are here to talk about embedded systems, microcontrollers, and such. And so there was this discussion about how to go about this, what should be the topic, and we talked about latest trends. We talked about, and I started thinking, is it really can I predict where the world is going? I cannot tell you what the trend is. The trend changes. In the last 2 years, the trend is AI. I mean, who had seen that coming, right? So we cannot, but we can only see how evolution has happened and really position ourselves for learning in the future. We cannot just say, "Hey, I know the trend and I'm going to follow this." And so just remember this as the starting point. I'm going to start. There are a lot of students. Are they all muted? I would like some participation. Help me out here, guys. So don't know. I see some are third year, some are first year, and things like that. So uh, I will go to this slide. So let's talk about a computing system. Let's discuss a computer system. And here is a computer system. And what I've added to a computer system is two other things, which is the sensors and actuators. Generally, we learn about computers, and I'm assuming many of you know more than me about computers, whether what the CPU is in the latest CPU, the memory, the storage, the display. And then I've added two other things to it, sensors and actuators. And this is generally also, in my computer, I have sensors and actuators. I have a keyboard, which is an actuator. I have a display, which I have a camera right now. I have a microphone, which is a sensor, and that's generally always a computing system. Let me ask you a question here. Is this computing system, can this computing system be called an embedded system? If I just had this picture. Anyone? Everybody's muted? Yes. Go for it, Anuk. Is it an embedded system? Okay.
Yes.
I think I have a. Don't everybody start talking at the same time. Go ahead, Aryan. You want to say something?
Yes, I think it's embedded system.
Is
It is an embedded system.
it is embedded system? Okay. So let me switch gears, and I think I'm going to need some participation. I'm going to ask you that we need to design a board for the rowing team. You know, rowing team, the row people who row. I want you to think about a boat for the rowing team. What comes to mind? what kind of boat would you design? If you were asked to design a boat for the rowing team, what kind of boat will you design? Anybody? Very quiet group. Okay. All right.
You can unmute, guys. You can unmute yourself and then talk.
Yeah. Participate. Don't let it be just one person talking. Okay. In the interest of time, I'm going to bring this up. This is Google Gemini, and exactly the question I gave you. I told this to AI agent: design a boat for the rowing team. Show a picture. Okay, and you can see the prompt is right here. This is the prompt, and then design a boat for the rowing team. Show a picture. This is the prompt, and so let me open it. What it will do. It built me a picture of a boat like this. Okay, I want you to think about this for a minute. This is what it did. Why did it do that? What forced it to do it? What was the thing that it knows, and what is the mental model it uses? I believe 80-90% when I asked about this question thought of something like this: a long boat with people in a row rowing. Every one of you most probably thought like that. Very good. That's what we expect. So I told it's a four-man team. So first thing, we did not ask a question. So now I say, hey, it's a four-man team. And we have a world champion rower. Where to put him? So now you have more information. And now Gemini says, okay, this. It gives you a lot of details why it should be in the middle, in the end, whether he has this skill, that skill, all this. Very good. All this is very good. Show me a picture. So it makes me another picture of four people on a rowing boat rowing. Okay. Are you guys with me still? Everyone with me? Okay. So now let's think about it. Why is the boat long and the rowers in a single file? Why? Why did you design it this way? And then it gives me all the reason why the boat is long. Because of aerodynamics, because of surface area, because of frontal thing, the vector of speed and the slipstream, and the effort is gained because everybody rows in sync. But here is a problem. When I ask you to design a boat, I never specify that the objective is to go fast. I never specified the objective. I just said design a boat for the rowing team, and we all assume we have to go fast. The objective is not to go fast. So then it says, yes, absolutely, I jumped. I'm sorry. Just like every AI and every student and every engineer most probably has this problem. They'll go through this. And then it has this endurance and design and all these things. So where should we put the thing? So the goal is to hold the boat in one position. So the goal is to hold the boat in one position. The more it deviates from its starting position, the team loses. Design such a boat. You see, now the whole framework shifted. We said design a boat, and then now we have more details, and now we have to design a boat. Guess what the boat shape would be? That is so fascinating. It's an engineering challenge, and then it goes through it, and I'm going to, in interest of time, cut it down to the picture that it showed me. I believe I can open it, and it became a boat which is square, unlike any boat you have ever seen. So when I was asking this question, we said it's an embedded system, and nothing wrong. It is an embedded system, except there is some other specs that we need to know about. So let's talk about this. Move to the next slide. Okay, so now we are talking a little bit more detail. So you have the same system. There is a paradigm that we have to do. There is a traditional computer. It's a general purpose computer. What is the goal? Flexibility. We have flexibility. It's designed to run multiple different software: the Zoom, the Word, the PowerPoint, the CAD software, the video, whatever you want to do, the web browser, everything. It can do everything. And of course, because of this, it needs a high performance CPU, gigabytes of RAM, and unlimited storage. It is human centric. It is designed to not just, you cannot just bring some sensor and put it in. I cannot just connect my microwave to it. Of course, today with Wi Fi you can, but you cannot just do things with it that require some changes to the hardware. It's not possible. It's designed to be human centric, human in the middle, right? And then if you were to look at the embedded system, it is designed for specific purpose. Its goal is efficiency. It is designed for a single repetitive task. It needs to do something and it needs to do that well, right? That's what it is. Resources, many of the embedded system today are low power. Your phone, I mean, we look at the battery life of a phone like as if that our life depends on it, truly. And so it has to be optimized. The longer the battery, the better it is. You know, the hand wristwatches, stuff like that. You know, the old wristwatches, we did not change battery for a year. And today with the Apple, you're okay with recharging it every day. So you see the paradigm shift there. So every memory matters, everything matters there. And then it's system centric. And many times it's headless, meaning it needs to just work and there is no human looking at it. I have a thermostat here, the thing that controls the temperature or AC. It just works, right? So many things that we encounter, they just work. You have sometimes systems that are monitoring patient in the hospital. They need to work, and you won't see a traditional computer there. Most of the times, you won't see. You'll see this monitor with heartbeat and pressure, and I don't know how many other things they monitor. But it has a very specific purpose, very specific type of display designed for efficiency, very specific type of memory, very specific type of computer and CPU. So this is the main difference between the two. So if we were to ask this question of goal, that's how we define the embedded system. So generally it is comes down to size, power, and the purpose. What is it going to do? What are the input output systems? In fact, all this being equal, what matters is the sensors and actuators in those cases, because most embedded systems want to interact with some outside agency, some outside sensor, something physical that you're measuring, controlling, monitoring, and taking action on, right? So, very good. So there is this engineering constraint and this divide. There is a very clear divide. So let's talk through this. Traditional laptop server that we have, I think everybody knows the spec: 19 watt to 200 watt main supply power, some kind of memory, 32, 32 is better than 16, which is, 64 is more is better, more is better. We want big storage, terabyte, 2 terabyte. How much can I get? The resolution of the display, bigger, 4K, 30-inch monitor, 50-inch monitor. Operating range is generally home use, and then reliability, people don't expect it to be reliable. It's if it requires reboot every couple of days, no big deal, right? Something. I'm saying 99.9 because computers have got better, but yeah. An update cycle, of course, you need frequent patches and this and that, and new updates come. But now you contrast this with the embedded system. So anybody has a guess? Again, questions up for what kind of power, memory, storage, display. Take any one and tell me what are we talking about here. If it was an embedded system, imagine it was a defibrillator. You know, the heart pumping machine. What kind of power you would need? It's battery operated generally. 10 watts, 5 watts, something like that, right? So let's just look at this. So in these cases, around 10 watts. Active peak power is around 10 watts. Microampere, they need to be deep sleeping. The defibrillator doesn't need to operate all the time, but when it needs to operate, it needs to operate. So that's what that is. The memory is somewhere in the megabyte region, right? So the gigabyte versus megabyte. I mean, think about it. And some even less in the kilobyte region, because you don't need, there is a shoe, there is a running shoe which has an embedded chip in it that'll measure your speed, your gait, your things. It needs only few kilobytes of memory, but it has to work, and it is battery operated, and it's embedded in the shoe. You cannot even replace it. You have to throw away the shoe. So it needs to work for a couple of years continuously. So there is storage. Again, we are not talking terabytes of storage. We are talking somewhere if it's a gigabyte or 4 gigabytes, it's more than enough in many cases. High resolution. So displays are high resolution. In this case, it's headless. Headless means it doesn't have any display, just does the work. A carbon monoxide detector just does the work. When it detects carbon monoxide, it starts beeping. It has nothing else, no display, nothing. Maybe it has a couple of buttons to set it up, and that's all there is. Um, an operating temperature, of course, it needs to be working at a higher temperature because sometimes these things are outdoors, right? So they need to be outdoors, indoors, and they are mission critical, fail safe, always on. They need to be always on. There is no reboot cycle. And then some of these things will be certified, meaning if you are going to be in a medical device field, it needs to be certified. If you are in, I'm in an oil and gas field, you're going offshore, it needs to be certified for hazardous gases and stuff like that. In many cases, it needs to be certified. So different requirements. Computers generally don't need to be certified. However, if you use a computer in oil and gas, it needs to be certified. So that's where that is. I will switch this to where we are with the CPU. So let's talk about CPU. I'm doing on time. We're okay. So we are talking about CPU, and you can think about like where it started. We used to have a Nintendo Game Boy. I think it's before the students were born in 1980s. This used to be a display with a little green screen and a little Mario jumping up and down, things like that, with a few buttons. And this was the latest and the greatest in the 80s. And basically, it's an 8-bit architecture. So it has an 8-bit bus. The CPU is 8-bit long. And then in the 2000s, we introduced the 32-bit ARM Cortex processor, which basically jump-started technology evolution to the next level, which was the Apple iPod, which is where we still had the screen was very minimalistic. It has the touch screen. One of the things that it had was a touch. You could do things with touching there was no buttons, but you did it everything with touch. And so the sensor technology was totally different from the prior generation. And then we introduced this asynchronous multiprocessing, AMP, where we can do multiple things at the same time, listen to Wi-Fi, and at the same time monitor a temperature, at the same time monitor the display, things like that. Also maybe a room sensor as to what it's doing. So multiple sources are coming in, you need to process it. So multiprocessor. And today we have, and I don't know if you guys have seen these autonomous robots. They're here in Dallas and other places. They deliver food. I mean, it's not Zomato and Swiggy like India, but they do deliver food in campuses, in neighborhoods. They are very, very good. I want to show you a video here at this point. Okay, will this work? I don't know. I'm going to show you this video of Micro Mouse. This is a very interesting video. If you get chance, go to YouTube, look for Micro Mouse, find the longest video you can find, and go through that video. It will blow your mind. I guarantee you. So, but I have taken a liberty here. Give me a second. If I play this sound, if I play this video, will the sound go through to you guys? I have no idea.
Try it, Ketan. Let's see. Yeah, no sound, but we can see the video.
Only audio is coming through?
Only video.
Only video is coming through. Let me see if I can do this. Share screen. There is a share button somewhere. Let me just see. Hide meeting, layout, pause, share, chat, video. No. More. Share computer sound. Okay. I'm going to restart the video. Okay, now the voice should come through.
This tiny robot mouse can finish this maze in just 6 seconds. Whew. Every year around the world, people compete in the oldest robotics race. The goal is simple. Get to the end of the maze as fast as possible.
The person who came second lost by 20 milliseconds.
But competition has grown fierce.
When somebody saw my design, they said, "You're crazy."
Why is there so much tension? What's riding on it? Honor?
Honor?
はい、まず昨年のこの大会ですね、全日本マイクロマップ大会の
マイクロマップ
サイズ競技部門で優勝してまして、去年作ったロボットからさらにブラッシュアップして作ってきたロボットで今年も連覇狙っていこうと思っています。
Even people in the top 2 or 3, you can see them trying to set their mice up and they can barely find the buttons to press because it's absolutely nerve-wracking. It doesn't matter what it was. It could be horse racing, it could be motor racing, it could be mouse racing. If you have a shred of competitiveness in you, you want to win, right?
The maze itself is a square about 3 meters on each side, subdivided by walls into corridors only 18 centimeters across. And in 2009, the half-size micromouse category was introduced, with mice smaller than 12.5 centimeters per side and paths just 9 centimeters across. The final layout of the maze is only revealed at the start of each competition. The micromice is to spend their first run.
I'm not going to go into all the details. You can still hear me, am I right? So I'm not going to go into all the details. I implore you to go watch the video. The mouse is very small. As you can see, there is a coin here and there is this part here. All the different pieces, they all have to fit into a mice that's about twice the size of this coin in roughly. But that's what an embedded system is. It requires the algorithm, the CPU, the processor. Everything else has to fit in there. There is wheels, there is motors, there is sensors. It needs to know where the wall is. It needs to move fast. It has a lot of criteria that it needs to do. So shifting to memory and storage, again, things are evolving in the embedded industry. The memories now, because before you used to need a RAM to load your program and then run the program from the RAM. Nowadays, you have execute in place. You have a memory. You never have to load the program. You don't have to have a shadowing RAM, so to speak. You can directly read from your ROM, so to speak. And so there is execute in place, which is these RAMs are so fast that you don't need to do that. And then these magnetorestrictive RAMs, non-volatile memory, these things are very, very good. The main problem of other memories used to be their longevity. They lose, sometimes you get corruption, sometimes you don't get. So static RAMs had the problem of that. And so this MRAM, there is infinite endurance. Once written, you'll always have the same code. You can load and read and write for millions of cycles, right? And then, of course, universal flash storage, the high bandwidth cards, multimedia cards are available. They're small in size, like your SIM card, and they can be put in on your system. So we can make a very small micro mouse because of these advances. So these are some stuff that is happening in the industry as we go along. One other thing, the legacy buses. In the old days, we used to have I2C, SPI, UART. I don't know how familiar you guys are with these protocols, but these are getting replaced. I think 10 years, 15 years ago, we had time-sensitive networking. Ethercat got introduced, which is low latency, high packet bandwidth on an Ethernet-like system. And nowadays, it's all wireless fabric. I think you need to learn wireless, low power, wide area networks, and Bluetooth low energy, because things are moving fast. Bluetooth is limited by distance, but there is this NB-IoT, which is the no bounds IoT, which is going to increase this distance. So you can wirelessly communicate with other devices. And nowadays, the embedded system does not work by itself. It is always connected to its home, to a cloud, to a server, to something that has more control over it. So these are certain things, how things are evolving. So for you guys, you definitely need to figure out the wireless piece here. And then there is a memory safety and languages. So software stack has also evolved. There was a language, came from Algol, then there was a B language, short-lived, then there was C. And C has been around for a long time, and it is the preferred language for embedded systems. Of course, there is C++, and this is, I'm talking high-level coding. I don't think anybody is doing assembly language code and things like that. But we are all writing in C++ or some similar language. And now we need the memory safety. And so the shift is from C to Rust. And I don't say go and learn Rust, but Rust, the learning curve is large and the people using it is small. So don't go out and learn it, but that's the shift that we see that is going from C to Rust. Rust is a programming language. And then hypervisors, where you want something like an operating system on your computer with real-time capability. So we have a real-time operating system. Zephyr comes to mind, Zephyr, and then you can have non-secure Linux or any other system that can run. But multiple operating systems, you can have an operating system and a fixed code run together on the same CPU fabric, and so that's the hypervisor idea. And then there is this WebAssembly that may come for different things. One other thing is hardware in the loop verification. Won't go into details, but if you do go to industry, this is something that many people are doing. And that is evolving into software in the loop rather than hardware in the loop, because hardware in the loop is generally very expensive in some cases. So that is also evolving. So this is where the memory piece is going, the software piece is going. Let's look at the AI. Of course, everything has to be AI, edge AI. So there will be a AI at the edge, in the sense there is an embedded system, wireless network connected to the cloud. Somewhere in the middle, there is an edge. It can be on the embedded system or it be edge of the cloud. And where this tera operations or 10 tops, tera operations per second. And so this is where you're doing the real-time vision recognition, because you need the library of images, and we don't need a cloud latency. I see this. Is it a leaf? Is it a stone? What is it? And so I send the image, and after 10 seconds, I get the car will stop. So you need a library somewhere. There is an edge very close to you, and this is where you need the tera operations per second. Yeah, and so this is important. And then so the modern architecture is generally NPU or a matrix acceleration hardware, which is N is the numerical processing unit. And why do you think we need numerical processing? Because today's world, you have to process a lot of data and you have to do a lot of math. It is not just binary logic on, off. I'm going to turn a timer on, off, a timer, a presence and absence of information. It has moved from there to you're doing regression, you're doing machine learning, you're doing some kind of an AI sort of thing. So you have that arithmetic logic unit, you have the hardware security because you don't want people to tamper, and then you have peripheral data, so direct memory access or any of those other things that may be present. And then there is this lockstep CPU, which we call redundant cores. So we always, in an embedded system, if you're going in an oil and gas field, if you're going to medical, if you're in an autonomous driving situation with a car, or if you're also making defense pieces, a landmine, for example, all of these need redundant hardware. So remember this, it's multiple cores and multiple memory units. This is all in this presentation. If I shared it, I just wanted to make sure I have an acronym glossary. And then, this is my professional summary. Aside from what Vaishnavi said, I do want to, it will not come across because last 20 years I've worked in energy industry. But before that, I've also worked in broadcasting, radio, television, RF microwave, and medical devices. So AI will not tell you about this. May not tell you about many other things, but this is just my summary. So the last takeaway, embedded design is the art of achieving maximum reliability with a minimum resource footprint. So you want to maximize your compute, maximize your memory, maximize your reliability in a smallest possible footprint. So with that, and open up for questions.
Yes, students, you can unmute yourself, and if you have any questions.
Ooh. Anyone? Don't everybody speak at the same time.
Yes, anyone can ask the question. Students.
Sir, what could be the career option in this field of embedded systems? Seeing the recent trends.
I think so. Let me say this way. Whatever you learn in the thing in your career, you will have to evolve. What I learned, I don't live in the world where what I learned. I live in a world where it has evolved. So the point is that whatever you come, you will start your career, but you will always learn along the way. In the world of embedded systems, where you have a regular computer, you sit at a computer and do, this is one thing, there is career there. The path gets a little bit where there are only few people who take this idea of having a compute and move to the small, I'm going to make a device, I'm going to make this, it's going to go in a chemical factory and it is going to monitor this and do this. This area, the number of people is less and the work is huge. So the career option in terms of if you're thinking about job and everything else, there is lack of people in that area. So you will have to make, you will have a good career, let's call it this way. I will not say money, but you will have a satisfying career if you like this job. If you don't like this and if you're pursuing monetary things, then I would say then they are better off in other areas in that sense. Not that you will not make a lot of money, you will make a lot of money. But the question is, what do you, maybe you, finance has better money. So do you move to finance? In life, you want to do things that you like to do. You want to do things that you love. And you realize it that no amount of money is going to substitute this happiness you get from it. So that's where I would leave it. But there is a lack of people who can take this idea of compute and bring it to a factory floor. So plenty of jobs available, plenty of learning opportunities available. AI is going to be in every device. If you didn't believe it, it's on my phone now. Gemini is on my phone 24/7, and it's going to go even into smaller. I have a microwave, there is Wi-Fi in it. I'm very sure there's going to be a Gemini there watching over. I don't have to learn to cook. I have a fridge which has a camera inside. It tells me what my shopping list is. It is going to get better. So all these things, image recognition, if you think of algorithmic development, if you watch the video, the one I said, if you watch that video, you will realize what kind of thinking goes into making such a system. And this is the rewarding part. So money is there. Don't worry about money. Money is there in all the fields, no matter where you go. Anything else? Any other questions? I would have thought that you would have a question on the fact that we showed you a micro mouse, but that's just a student project or competition project. Somebody would say, hey, how do you use it? I saw your bio, it doesn't match with embedded system or something like that. If nobody asks, I will not answer.
I'm sure students will have questions. So Manali ma'am, you can gather their questions. If you want, you can shoot them to me, and
Yes.
I'm sure Ketan, you would be happy to answer offline also.
Yes. Any other questions, students? Otherwise, we can start with framework.
Sure. Again, Ketan, thanks for your time. I'm sure students learned a lot. We will go to the next topic today. Ketan, can I share my screen? I think if you stop share, then I'll be able to share.